let's solve this fairly straightforward circuit problem, but it'll help us understand how to solve more complicated circuit problems. And I just made this up so the numbers may be whack. I don't really know, but we're going to do it anyway. Nothing's going to stop us. So in this circuit, I have two batteries, a 5 volt and a 10 volt, and then I have three resistors, a 10 ohm, a 20 ohm, and a 5 ohm. Notice the orientation of the batteries. This one has the positive side on this side. This one has the positive side on that side. So not that it really matters. I just picked that just to kind of like, spice things up a little bit. Now, a lot of people may take a problem like this. I need to start staying on this side. I think it looks better. A lot of people may take a problem like this and say, hey, I could do combination of resistors. I could combine the resistors and make it a simpler problem. And sometimes that is true. However, in this case, we do not have any resistors that are in parallel. We do not have any resistors that are in series, because these are not in parallel because their voltage across them is not the same. The voltage from here to there is not the same as there to there because of that 5 volt battery. And the same thing's true down here. And then these are not in series because there's a junction in between them. So nothing is in series, nothing is in parallel. You can't make an equivalent resistance here. Okay, so let's go ahead and see how we would solve this. So number one thing we want to do is, when we say solve a circuit, we mean what is electric current. So what is electric current in this circuit? Well, there's three different currents. So let's just pick values for the current. I'm going to say this current coming out of the battery right here, I'm going to put it right here, is I1. And then I'm going to say at this junction, some of it goes this way, I2, and some goes this way, I3. I don't know if those directions are correct. I'm just kind of picking, right? If they're wrong, we'll find out at the end. So with that, I have three currents I need to solve, right? Because there's no other currents. That current is I1. This current is I3. That's it. I only have those three. So if I have three variables I'm trying to solve, I1, I2, and I3, I'm going to need three equations. So three equations. Let's get three equations. The equations come from two things: the junction rule and the loop rule. So let's look at the junction rule first. The junction rule says that all of the current coming into a node where currents meet have to satisfy the condition that the total current coming in and the total current coming out have to be equal. If that wasn't true, remember, current is the motion of charge. If there's more charge coming in than leaving, there would be a charge buildup there. And these are in equilibrium conditions, so we're not going to have charge buildup. So that means that at this node right here, I could write the following equation. The total current coming in would just be I1, and then the total current leaving would be I1, I2, and I3. So I2 plus I3. And that's an equation for those three variables. Now, I could do this junction over here. That's the only other junction I have. However, this would be I2 plus I3 equals I1, which is the same thing, right? So it doesn't really gain me anything. Now, the other equation that I'm going to get from the loop rule. Remember that when we look at electric potential, the electric potential, because it's a potential energy, once you multiply it by a charge, has to be path independent. And since it's path independent, that means if I go around in a complete loop, you would have to have a change in potential of 0. So the loop rule is essentially part of this conservation of energy idea. And it means that if I take the loop around any of these loops, I actually have three loops, right? I could go here, I could go here, I could go here. And if I add up the voltages around any of those loops, it has to be 0. Now, I don't need three loops, right? Because I already have one equation. I need three equations. So there's one, I need two more. So I just need to get two of those loops. And you may think, hey, what if I just do three loops and no junction rules? If you try that, the three equations will not be linearly independent and you can't solve. You would get down to something like 1 equals 1. So you can't do that. You could try, but you can't. So in a loop rule, there's two rules. Number one, a battery. So if I go from the negative to positive side of a battery, I get a positive voltage drop or change. If I go from positive to negative, I get negative. So the orientation matters. Second, V equals IR. that's the voltage drop across a resistor, is I times R. If I'm going in the direction of current, then it's a negative voltage drop. If I'm going in the opposite direction, it's positive. So let's write down the loop rule for, I'm going to do 2 loops. I'm going to do this one. I'm going to start right here. I'm going to go around here. Let's do the loop rule. So if I start here, I go across this battery. I'm going from negative to positive, so I get 5 volts. I'll leave off the units. And now I'm going in the same direction as the current, so I get a voltage drop minus 10 I1, right? I times R. And then I come down here, and then I'm going this way. Now I'm going in the same direction again as the current, but I have current I2, so I get minus 20 I2. And then I get back to where I was, 0. So that's an equation with I1 and I2 in it. Then I have an equation up here with I1, I2, and I3. Let's do this loop down here. So if I do this loop, I'm going to go up here. I'm going to go across this resistor, but now I'm going in the opposite direction as that current. So I'm going to get a positive voltage change, and that's going to be 20 I2. And then down here, I'm going to be going in the same direction as I3, so I get a voltage drop of minus 5 I3. And then I'm going in the same, I'm going from negative to positive across that battery, so it's going to be plus 10. And then I get back to where I started, 0. So I have 1, 2, I have 3 equations and 3 unknowns. So I can solve this system of equations. Now, this is a system of linear equations. So they're linear because all my variables are just raised to the first power. I don't have squares or square roots or sines or anything like that. So that makes it a lot simpler to solve. And there are multiple methods you could use to solve this. You could use the matrix idea, reducing a row reduction for a matrix. You could add equations together or subtract equations. But I'm just going to do the old-fashioned way that always works, and that is to take substitution. So right here, I can take I1, and I can substitute it into these 2 equations whenever I see I1, and then I'll have 2 equations, 2 unknowns. So that's the way I'm going to do it. Let me go ahead and write these 3 equations over here. I1 equals I2 plus I3, and then I had 5 minus 10 I1 minus 20 I2 equals 0. And then the last one was 20, can you see that? Yeah, 20 I2 minus 5 I3 plus 10 equals 0. Now I can erase this stuff, and I can work. Sometimes I write things too big and I run out of space. Okay, so right here, I've solved this equation for I1. It started that way. So I'm going to rewrite these 2 equations, but instead of I1, I'm going to put I2 plus I3. So this first equation is 5 minus 10 I1, which is going to be I2 plus I3. And then I have minus 20 I2. And now the second equation doesn't have an I1 in it, so I'm not going to write that yet. Let's just simplify this. 5 minus 10 I2 minus 10 I3 minus 20 I2 equals 0. And then I have a minus 10 I2, I have a minus 20 I2, that's minus 30 I2. So I have 5 minus 10 I2, no, I said 20, not 30, minus 30 I2 minus 10 I3 equals 0. Okay, so now I have an I2 I3 equation, I have an I2 I3 equation. I'm going to need to solve for one of these and substitute into the other. I'm just looking to see if there's something nice. There's nothing nice. I'm going to solve this one for I3. I don't know why, I just picked it. So I'm going to add ten I3 to both sides. So I get 10 I3 equals 5 minus 30 I2. That's it. I'm going to divide both sides by 10, and I get I3 equals 0.5, right, because 5 divided by 10, minus 3 I2. That's why I did it, because I could do that in my head without my calculator. So now I have an expression for I3. I can substitute that in down here. So let's write this equation, and instead of I3, I'm going to put that. So right here I have 20I2 minus 5I3. So minus 5, and then I3 is this, 0.5 minus 3I2. And then plus 10. Okay, so now I have an equation that only has I2 in it. Yay. Okay, so I can solve this. Let's just do this. Let's multiply this out. I get 20I2 minus 5 times 0.05 is going to be 2.5. Did that in my head. You can use your calculator. And then I have minus 5 times minus 3I2. That's going to be plus 15I2. And then I have plus 10. So I have a 15I2 and a 20I2. So I'm just going to erase that and use the magic of chalk. And then I'm going to add negative 5, 2.5 and 10. And that's going to be 7.5. Again, just doing it in my head. And then I can subtract 7.5 from both sides, and I get 35. That was 35, right? Yeah. 35 I2 equals negative 7.5. So I2 is going to be negative 7.5 over 35. Now I am going to use my calculator, which I left over here. Okay, so I have 7.5, 35 divided by, I get negative 2.14. No, 0.214. And that is I2. So notice that it's a negative. That means that I got the direction wrong. So I2 is actually going that way. Negative I2 this way is the same as positive I2 that way. So you can either change the direction or just at the end to say negative 0.214 amps. That's fine. But what about the other currents? Now we can go back, right? So now I can start working my way backwards. I know the current I2, and so up here I can plug in I2 and solve for I3. So I have 0.5 minus 3 times negative 0.214. And that is going to give me, again, I'll put it in my calculator. So I have 0.5, and then negative is positive. So I'm going to say 3.214 times plus, and I get 1.142. And that's I3. I'm going to put a box around that, and this is the box 2. Now I can find I1. So I'm going to go back way over here to this equation and just say I2 plus I3 is I1. So it's going to be equal to 1.142 minus 0.214. So I can just do minus, and I get 0.928. Box. So we did it. We solved this problem. Now, and like I said, this is simple. It can get more complicated. You could have 4 unknown currents, and you'd probably have to have 2 loops or 3 loops. There would be 2 loops and 2 junctions. Well, I'm not sure. It depends on the circuit. But you'd have 4 equations, 4 unknowns, and you can use the same idea. It just takes longer, and there's more chance for an error. I think, but if you understand this, doing more complicated is really the same thing, just different. So it's not that big of a deal. So there you go. Solving an equation, a system of circuits.